To solve problem 3-139, first we want to draw a diagram for where the knowns are. So we have a fin, it's 50 millimeters in diameter, and then we have the sides, which are 90 millimeters. First we want to find the heat transfer of the pipe, and that's given as 2k pi Ti minus Tb over L and d naught over di, and then your efficiency for convection equation. So then you can solve for Tb by changing this equation, and we'll use this later. So first, from table 3-3, we want to determine the R and area final. So the corrected radius is this equation, and we get 0.055 meters. Corrected area is this, and then our corrected length is just L plus R radius, so T over 2. And then we can get our squiggly, which is the given value needed for our efficiency. We get 0.198, solve for efficiency. From the table, you get 0.98, and then use the equation above to get Tb, the base temperature of the fin. Then we can solve for the final heat transfer rate, and that's just what we used above, and you get 16 watts. This can be repeated for the different temperatures and dimensions of length, and that's just what's shown here. For 3-197, we have our knowns, which is this written here, and the temperature of the tip is 250 degrees C. So we want to find the heat transfer of various things. We can use the equations given. And as you can see, first you want to find the perimeter, the area, and then M. And then these values are used to find the Q, heat transfer of a long fin, adiabatic tip, and your final temperature profile, which is given in the equations. So there is a plot above that shows you this. Next we have known, 3-202. We want to find the resistances. So the resistance of the board, which is a material property, is L over Ka, and then our convection is 1 over Ha. Plug in those values, and you get 1.48 degrees C per watt. Then we can find our heat transfer, which is equal to our Q dot times R plus our temperature, just resolving for T1, and that's 59.4 degrees C. Then you can solve for M. You get your efficiency from that with your given equation. Find the area unfinned. This is just based on what the figure looks like for how many fins there are. And then the area unfinned, also based on that. We can find our Q dot finned by taking our efficiency times our heat transfer rate, and then our Q unfinned without the heat fin efficiency. Then add those together, you get your Q total. You want to find your T base, which is equal to this equation. Plug in those values, you get 39.5 degrees C. Our resistance of aluminum is given as L over Ka, and then the epoxy, same idea, get two different values. Then you can find your overall heat transfer rate by taking your difference in temperatures over your resistances. So you get 39.8 degrees C. Then your total heat transfer rate is just over the board. This is without the fin, or without the insulation here. You get 39.6 degrees C, which is not a big difference. What I did not understand in these problems is this plot was difficult for me to make. In the end, I figured it out, but it took a while.